Hello, my name is Jade Louie, and I'm a PhD student from the University of Glasgow. My presentation is on the techno-economic and life cycle assessment of waste-to-hydrogen technologies in Glasgow, Scotland. I will discuss the potential of using waste-to-hydrogen technologies using Glasgow, a city in the central belt of Scotland with a population of around 620,000 people, for both hydrogen production purposes and as a waste management strategy. Waste-to-hydrogen is a hybrid solution which can tackle sustainable waste management as an alternative to landfill and incineration for waste disposal, and also as an option for hydrogen production as an alternative to the conventional steam methane reforming. Waste management is a sector that produces large CO2 emissions and requires decarbonisation to help deal with climate change. And waste-to-hydrogen can be an important tool for low-emissions waste management schemes and policies. A landfill ban will be introduced in Scotland from 2025, as about 7.2 million tonnes of biodegradable municipal waste were sent to landfill in the UK in 2018. The EU in 2012 lost the potential energy of over 3,000 petajoules through unsustainable waste management schemes, and is an example of the importance of changing the view of waste as a resource. Decarbonisation is an important issue, as shown by the Scottish Government announcing climate emergency in 2019 and introducing emissions targets such as the net zero emissions by 2045 and a commitment for clean energy generation to reduce the impact of CO2 emitting industries such as transport. The UK Department of Transport released the Decarbonising Transport report, which states that the application of hydrogen in the transport sector is one of the main methods for carbon abatement. The UK Hydrogen Strategy, released in 2021, sets out the UK government strategy on increasing the production and use of hydrogen as an alternative to fossil fuels for transport applications, as hydrogen is a zero-emissions fuel when used in fuel cell electric vehicles. Waste-to-hydrogen technologies included in the study are gasification as the thermochemical technique, which produces a synthetic gas from heating feedstock at between 850 and 1,000 degrees centigrade. Gasification was chosen due to the state of its technological advancement and the ability to handle a range of feedstocks. Here I consider it for waste wood products, municipal solid waste, and other solid wastes with low energy density. There are a range of gasification reactors available. The system diagram here illustrates a circulating fluidized bed reactor. For the biochemical technology option, I have included dark and combined dark and photo fermentation, which is ideal for high moisture content wet waste categories, such as sewage sludge and food waste. The process has low energy requirements compared to thermochemical technologies, but produces lower hydrogen yields. For this study, I created 5 scenarios of gasification with municipal solid waste, gasification with waste wood products, dark fermentation with wet waste, and combined dark and photofermentation with wet waste. For a comparison scenario, I used steam methane reforming as the conventional hydrogen production technology, which is the catalytic reforming of methane with steam at temperatures of 850 to 900 degrees C and pressures of between 20 and 40 bar. The table details the type and quantity of available waste from Glasgow for these technologies. Recyclable material, glass and metals have been excluded. The economic assessment is designed to test the feasibility of the waste-to-hydrogen technologies using the quantities of available waste in Glasgow, shown in the last slide, providing the setting from which costs were calculated. A database of direct and indirect costs as CAPEX, OPEX and tax was gathered. The energy requirements, which were supplied by the UK electricity grid for the equipment and operations, was also collected. Hydrogen yield as the final product is used as the benefit parameter. For the cost-benefit analysis, we calculated the net present value, levelized cost of hydrogen, internal rate of return, and benefit cost ratio. It was concluded with a sensitivity analysis to highlight the most sensitive parameter for costs in the system. The results are illustrated in the graph on the left, with total costs against each scenario, and the levelized cost of hydrogen as the red crosses. This graph shows the high cost of hydrogen with all the waste-to-hydrogen technologies, with the fermentation technologies currently having the lowest total cost. The comparison scenario of steam methane reforming has the lowest total cost and cost of hydrogen due to its advanced nature and wide-scale use. Though all the CBA results suggest the waste-to-hydrogen technologies are encouraging, with the MPV showing profit potential, the IRR indicating them to be attractive investments, and the benefits outweighing the costs. The graph on the right shows hydrogen production cost against potential profit. Differences in the gradients of the trend lines from the scenarios imply which technologies have potential for highest profit. The waste-to-hydrogen technologies start with a higher break-even point of expenses equaling income, followed by a steady increase in profit. Scenario 1, or gasification with municipal solid waste, has the steepest gradient and the greatest capacity for profit, even greater than that of SMR. In terms of the sensitivity analysis, NPV for the gasification scenarios 1 and 2 was most sensitive to changes in capex, while the fermentation scenarios 3 and 4 were most sensitive to low production rates as expected. I'm going to briefly mention the life cycle assessment portion of the study, as the environmental impact analysis complements the economic analysis. The life cycle assessment for each scenario has a system boundary of gate to gate, includes 2 different functional units of 1 ton waste feedstock and 1 kilogram of hydrogen produced, and the results are given in global warming potential units of kilogram CO2 equivalent per kilogram of hydrogen. Gabi software was used for the modelling and provided data along with other academic and industrial sources. A sensitivity analysis was also conducted. The results show that when using the functional unit of 1 ton feedstock, the global warming potential is markedly lower for the fermentation scenarios of 3 and 4. When using the functional unit of hydrogen produced, the fermentation technologies are higher than the gasification ones of scenarios 1 and 2. This is due to the large difference in hydrogen yield between gasification and fermentation, and may influence how the benefit of each is perceived. Steam methane reforming, unsurprisingly, has the highest global warming potential, no matter what the functional unit. The study shows the positive implications of waste-to-hydrogen technologies using waste as feedstock in Glasgow. Whilst costs are currently high, there is potential for profit, and waste-to-hydrogen can be attractive for investors. The environmental impact is also lower than conventional methods. Therefore, this type of hydrogen production and waste management can be part of the solution to decarbonise and help with the energy transition. Thank you for listening.
Dr. J.P. is not available online.
I would like to acknowledge and thank the University of Glasgow, EPSRC for providing student funding for the research, and Supergen Bioenergy Hub for funding and support.
JP is not available online because of COVID. If any questions, you can email her. And we'll like to thank JP for her important topic on LCA for hydrogen production. Please use So with this, we come to closing of this session, and I would like to thank speakers for their excellent talks, as well as for the audience for very kind support, and also